Okay, so we're going to work 10.5.2, 10.5.3. These are conceptual problems, but they're really important, okay? And it's a little bit of a problem solving, a little bit of a lecture here for this video. We're asked in 10.5.2 for a class of molecules such as AX sub n. This is the subscript. This is supposed to be something like a generic chemical formula in which n is greater than 2. How can we tell if a molecule is polar or nonpolar? And then the follow-up question is 1053. How can a molecule with polar covalent bonds possibly be nonpolar? So all these things kind of tend to work together. I have a flowchart at the bottom. We'll try to use that as we go. But let's kind of explain what we're talking about here, because this is actually another important concept. Okay, so first off, we're talking about molecules with this formula, AX sub n. A is supposed to be the central atom here. And in the Lewis dot structure for this class of molecules, we'd have something like this, X, X, and X, okay? Where these X are the peripheral atoms, and then this guy is in the center. These would be complete octets, we'll say. So dot, 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 dot. You get the idea, right? So this is kind of our Lewis dot structure for, where n equals 3 here. So this would be AX3. So we'd have a molecule of, this essential shape, basically, okay? We have something that's planar and trigonal, hence the name trigonal planar if I'm considering AX3, as I am right here. And, I'm considering this first question, how can we tell if this is polar or non-polar? And basically what that has to do with is charge distributions in the molecule that results from unequal sharing of the electrons involved in bonding. So in the covalent bonding model, each of these lines represent a covalent bond in which electrons are shared between A and any given atom of X. Now, the thing is that those bonding electrons may not be shared equally, okay? So for the purposes of this particular discussion, I'm going to shift away from this generic chemical formula business and give you a very specific example. For this particular class of compound, I may be talking about BF3 or boron trifluoride. Now, this would certainly be a trigonal planar molecule with the incomplete octet on the central boron. It's only got 6 electrons, but this is its Lewis structure. And again, it would have this type of molecular shape, okay? Boron trifluoride, trigonal planar, okay? Now, this molecule, I'll start off by telling you, would be considered non-polar or not polar. Now, how in the world can that be? Fluorine, we know, is a very electronegative element. It doesn't like to share electrons. It likes to hog those electrons for itself. That's what electronegativity means. So as a result, each end of this bond would be partially negative. The electrons are tending to reside around the fluorine more. The fluorine hogs those electrons, and consequently, the boron kind of gets the shaft, so to speak, and those electrons tend to hang out near the fluorine. Now, the thing is that for each of these bonds, I can draw in a similar bond dipole vector. Okay? And basically what that means is the fluorine ends are partially negative in each case, and the boron end is partially positive in each case. So chemists like to use these little delta positive signs for positive for the boron and delta negative for the fluorine. Now that's true for each of these bonds because they're identical. It's a bond between the boron and the fluorine. So you say, well, okay, I've got polar bonds, and they're very polar in this particular case, right? This is highly partially negative and highly partially positive for the boron, but how could this be a nonpolar molecule? Well, the trick is the molecular geometry, right? The molecular geometry. Fluorine, 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 they're here shown in white, okay? And the boron will be the purple in the center if I'm following this structure. I guess I should flip it upside down so it looks more like that. These arrows always point to the negative end of the bond. Okay, so there'd be an arrow here along this bond axis, here, and along this bond axis. There's 3 arrows, okay, one along each bond axis. And I'm wondering, have you ever, just try to give you an analogy here, have you ever played tug of war between 3 people where you might have a triangular rope and you put one person at this end, one person down here, one person here? What happens if they all pull exactly equally? The rope doesn't move anywhere, right? That's kind of what's going on here. If this bond dipole vector is equivalent to this one and is equivalent to this one, it turns out if you add those three vectors together, they cancel each other out. And there's no net dipole vector or no net molecular dipole vector. Now there's three bond dipole vectors. Every bond can possibly have a dipole vector associated with it. And I guess you could say that every bond has a dipole vector associated with it. Sometimes it's zero, I suppose, if you have the both element at each end of the bonds. But each of these bond dipole vectors sum to make the molecular dipole vector. And if they're all equal and they cancel each other out in three-dimensional space, the molecule is nonpolar. So BF3 is an example of a nonpolar molecule because each of these arrows are identical and they cancel each other out in three-dimensional space. And that's the kind of crucial key element that we're getting at here, okay? So how can we tell if a molecule is polar? Well, I think this flowchart is helpful for that. You start by asking, does the molecule have polar bonds? If it does, the molecule might be polar. But if the molecule does not have any polar bonds at all, that would be kind of an unusual case. The molecule is nonpolar. Now, what molecules kind of fit that category? Well, think about like N2. Okay, that'll be its Lewis dot structure, or like F2 or something like that. Fluorine, homonuclear diatomics, basically. That'll be a simple example of this category. They've got the same atom at both ends of the bond, so there's no difference in electronegativity. As a result, there's no polar bonds. That's a nonpolar molecule. Sure enough, these exist as gases, and that makes sense because they're not polar. Now, if the molecule has polar bonds, this is going to be by far the more common case. The molecule might be polar. The next question you have to ask, though, do the bond dipole vectors, these little arrows that we're just talking about here, do they cancel out or do they not cancel out? If they cancel out, the molecule is nonpolar. If they do not cancel, the molecule is polar. So again, these little arrows are vectors. They point to the negative end. The positive end is here, okay, at the base of the arrow. And I should also say the length of that arrow is important because the length of the arrow describes the degree of charge separation between the atoms making up the bond. That has to do with the difference in electronegativities between the two atoms. Now, these would be pretty big because there's a pretty big difference in electronegativity between these elements, so they're pretty substantial arrows. This molecule does have polar bonds. Each of the three bonds are highly polar. So if I'm following my flowchart, I'd say, yes, it has polar bonds. Do the bond dipole vectors cancel? Yes, they do. Because again, just like we had the tug-of-war between three people pulling equally, in such a case, the vectors cancel and we have a nonpolar molecule. Now what if I changed this? Okay, what would happen? Instead of fluorine, I put a different element at this one spot. Maybe I make it chlorine. It's another halogen. Okay? So I change the atom that's at one of the locations. And let's just say, oh, that's not going to be a good color to use. So let me find a new color for my molecule. Let's say that I make the chlorine yellow. Okay? So now, one of the three is yellow. Fluorine, fluorine, chlorine, boron in the center in purple still. Is this a polar or a nonpolar molecule? Well, I guess we can follow the flowchart. Does it have polar bonds? Yes, because there's a difference in electronegativity between fluorine and boron, as there's a difference between boron and chlorine. All these bonds are polar, okay? But do the bond dipole vectors cancel? So now we got to think about this, okay? So is this new bond between boron and chlorine polar? Yes. We'll say that chlorine is more electronegative than boron, and as a result, the arrow will point that way towards chlorine. But the question is do the bond vectors cancel each other? So we go back to this analogy now with the tug-of-war, right? The three-person tug-of-war. Earlier, those three people pulled exactly equally, and they neutralized each other. The rope doesn't move. What about now? fluorine is more electronegative than chlorine. So are each of these partners pooling equally now, or might they be pooling a little bit different? I think now it would be like pulling the tug of war where they're not pooling equally. This one's a little bit weaker, we'll say, right? So maybe there's still a net displacement in that direction in the case of tug of war, right? Well, in the case of molecular bond polarity, there'd be a net displacement of electrons. You could think of it that way. That would be a more polar molecule. So if I change any of the three and put something different there, I mess up the symmetry and I mess up this equal pooling, so to speak, okay? So that molecule would be polar, all right? So only if the bond dipole vectors cancel do I have a nonpolar molecule if I've got polar bonds. In all other cases, the molecule is going to have some polarity. So I can scale this all up away from just its trigonal planar geometry. I can talk about any geometry I want. I can talk about tetrahedral geometries, okay? This is the example of my tetrahedron, like carbon at the center. Maybe each of these are fluorines in green here, okay? Now, if I add up bond dipole vectors, even if this is carbon and fluorine, which would be a highly polar bond, if I add up the bond dipole vectors, if all four of these are the same on the outside, the green ones, they cancel. Nonpolar molecule. But as soon as I change one of them to make it a different element, maybe this is representative of iodine now, okay? As soon as I change one of them, I break the symmetry and it becomes polar. Okay, the bond dipole vectors no longer cancel each other, okay? There's a net dipole vector. All right, so if all of them are the same in your base geometry, if they're all present, all four are present, and all are the same, they can cancel each other out. But as soon as you change it and make something different, and maybe you can make a lone pair here. Maybe you don't need the iodine, right? That was there before. Maybe this is just something else, a lone pair. As soon as you break the equal tug of war, the molecule becomes polar, essentially. Okay? If I want to think about my square bipyramidal geometry, if all six are the same, nonpolar. But as soon as I change one for something different, I mess that up. Polar, right? So if you're able to cancel these individual bond dipole vectors, nonpolar. If you can't cancel, polar. Now they also want to give us, I think we're supposed to give some examples of different types of molecules where this type of thing is going on, okay? Let us go back to CF4, we'll say. It's a tetrahedral geometry, carbon at the center, pretend these green dots are F, or fluorine, right? If I have a perfect tetrahedral with all four of the outside atoms the same, my molecule is not polar because it doesn't matter what's there. The bond dipole vectors are always going to cancel if the green spheres are the same. So they can be fluorines and they all cancel. It's a nonpolar molecule, CF4, right? Now, would any one bond be polar? Oh boy, that'd be a very polar bond between carbon and fluorine. But it's just that each bond vector will cancel out the other three. Okay, if you sum all four together, they cancel. It's a nonpolar molecule. Another common example: carbon dioxide. Carbon, oxygen, oxygen. The reds are oxygen, the black's carbon. A double bond here, double bond here. It's an example of a linear molecule. Okay, carbon dioxide is nonpolar. Are the bonds polar? Yep, that's a polar bond. This is a polar bond. Just that they're identical. Carbon, oxygen, both are double bonds, right? So they're identical, and as a result of that, they cancel each other out. One pulls this way, the other pulls this way. It's like a tug of war with a straight rope in this case. CO2, nonpolar molecule, okay? So you got to consider both bond polarity and molecular shape when assessing whether a molecule is polar or nonpolar. So hopefully this video was useful for that.